Hello again. In this video, we're going to talk about the second derivative test, which is an alternative test that we can use to find local maximums and local minimums. Now, the reason I say an alternative test is because we already have a test that we can use to find local maximums and local minimums known as the first derivative test, which we talked about in a previous video. And we're going to compare the two in a moment. But let's talk about the second derivative test first. So here's what it says. Suppose the second derivative is continuous on an open interval containing c with f prime evaluated at c equal to 0. If the second derivative evaluated at c is positive, then f has a local minimum at c. If the second derivative evaluated at c is negative, then f has a local maximum at c. And if the second derivative evaluated at c is equal to 0, then the test is inconclusive, which means f may have a local maximum, a local minimum, or neither at c. Now, first of all, the second derivative test has a limitation to it. Notice that it can only be used to classify critical numbers where the derivative evaluated at the critical number is equal to 0. It cannot be used to classify critical numbers where the first derivative evaluated at c does not exist. And now let's talk about why the second derivative test works. So let's suppose you have a critical number where the first derivative evaluated at the critical number is actually equal to 0. There's only a few ways that can happen. So one way that can happen would be a situation like this. First derivative at c is 0 here, but it's also 0 here. So it could be this case as well. It could also be a case that looks like this. Okay, and so we need to figure out which case we're in. Okay, and here's how the second derivative test would classify the critical number. It's going to look at the concavity at c. That's why you plug c, the critical number c, into the second derivative. Now, let's say you take the critical number, you plug it into the second derivative, and you find out that it's positive. Then that indicates that it's concave up at c, and if it's concave up at the critical number, then it has to look like this. That means you have a local minimum at c. That's how it classifies the critical number. Okay. If you plug the critical number into the second derivative and you find out it's negative, then that means it's concave down at c, which means it looks like this, and therefore you have a local maximum at c. Now the other possibility is that the second derivative evaluated at c could equal 0, and in that case the test is inconclusive and we don't know whether we have a local maximum, a local minimum, or neither at c. Okay, so I just want to mention that the second derivative test has two limitations to it that I see. The first one is it can only be used to classify critical numbers where the first derivative evaluated at the critical number is equal to 0. And then the second limitation to the second derivative test is even in those particular cases where the first derivative at c is equal to 0, it may be that when you plug the critical number into the second derivative, you actually get 0 out. In that case, the test is inconclusive and you cannot tell whether you have a local maximum or a local minimum or neither at c. Okay, so having said that, the first derivative test, we're going to compare it to the second derivative test. The first derivative test has no limitations to it. So the way the first derivative test works is you find the critical numbers first, and then you classify those critical numbers by creating a sign chart for the first derivative, which tells you where the function's increasing and decreasing. So in this case, you would know you have a critical number here. And the way you would classify it using the first derivative test is you would take note of the fact that it's decreasing on this side and increasing on this side, which means you have a local minimum at c. Okay, in this case, of course, you have a critical number at C, but the way you would classify it using the first derivative test is you would note that it's increasing on this side and decreasing on this side, and therefore you have a local maximum at C. Now, if it were a case like this, right, you have a critical number here at C because the first derivative is 0 there. But when you go to classify it using the first derivative test, you would notice that it's increasing on the left side of C, but it's also increasing on the right side. Of course, it could also be the case that it's decreasing on the left and then decreasing on the right. So it could be a situation that looks like this. But then this is a case where you have neither a local max nor a local min, right, in both of these particular cases. Okay, so that's the difference between the first derivative test and the second derivative test. The first derivative test classifies the critical number by looking at whether it's increasing or decreasing to the left and right of the critical number. And the second derivative test tries to classify the critical number by checking the concavity at C. Okay, so let's do an example where we actually use the second derivative test to find the local maximums and local minimums. Okay, so let's do that for this particular function here. Let's find the local maximums and minimums using the second derivative test. Okay, so what do? Well, the first thing we got to do is find the critical numbers. And remember, the critical numbers are when the first derivative is either 0 or does not exist. Okay, so the first derivative in this case would be 3x squared minus 6x. Okay, now let's find the critical numbers. Now, we don't get any critical numbers in this particular case because the derivative exists for all x values. So this never happens. But if we did get a critical number from this particular case, you couldn't use the second derivative test to classify the critical number. You'd have to use the first derivative test to classify the critical numbers that come from this particular case. Okay, but we don't have any, so that's not a concern here. Okay, so let's look at the critical numbers that we get in this particular case when the derivative is 0. Okay, so here you would factor the 3x out, leaving you with x minus 2. And then when you go to solve this, you get 5 by 3, you just get x is 0. And then over here, you just get x is equal to 2. Okay, so we have two critical numbers here. Both of which came from this case. So we can actually try and classify these using the second derivative test since they're under this particular case. And the way you do that is you plug them into the second derivative and determine the concavity at these particular points. So let's find the second derivative. Okay, so the second derivative would be 6x minus 6. Okay, so let's try to classify this particular critical number by plugging it into the second derivative. And notice when you plug that into the second derivative, you get a negative 6, which means it's concave down. At that particular critical number. And if it's concave down at that particular critical number, then that means you have a local maximum at that particular x value. Okay. Now let's try to classify this one. Plug that into the second derivative, and you get 12 minus 6, which is a positive 6, right? So that means it's concave up at 2. Okay, and so it looks something like this, right? At 2, you have a critical number, it's concave up, so it's got to look something like that. And so that must mean you have a local minimum at 2. Okay, so let's just finish this off. Let's actually find the local minimums and maximums. Remember, because the local minimums and maximums are actually the y values at these particular points. Now remember, to do that, you're just going to have to take 0 and plug it into the original function to find its corresponding y value. So in this case, you get 0 out. Okay. And so this is actually at the origin. Like that. Okay, so that's the local maximum. Local maximum is 0, and it occurs when x is 0. Okay, now let's find the y value for this one by plugging that into here. So f of 2 will give us 2 cubed minus 3 times 2 squared. Okay, so that's 8 minus 12, which is negative 4. And that's our local minimum. Okay, so the local minimum is negative 4, and it happens to occur when x is 2. So this actually looks like this. Okay, so that's how you'd use the second derivative test to classify these critical numbers. Having said that, you can kind of check this by going to desmos.com, which is an online graphing calculator. Okay, so I'm just going to type in the function x cubed minus 3x squared, which looks like this. So you can see at this particular point, 0, 0, you have a local maximum, and then at this point over here, you have a local minimum of negative 4. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.